Alrighty, welcome class. Back to the section 4.1 notes. Sorry we were unable to finish it. Them because I'm not going to be there on Thursday. Again, I apologize. You're going to have to watch a video for the rest of the notes. You do have a practice day all Thursday. I just won't be there. So I suggest that you watch this video tonight or tomorrow, and then you will be all ready to practice with your other cohort of students on Thursday. So just a quick little review. Remember, we're talking about absolute minimums and maximums, or I like to actually refer them as global, and local maximums and minimums, which I refer to as local, but they also have the name relative, but I tend to go with the word local. Remember that maximums and minimums occur at three different locations. Either they're at endpoints, two locations, endpoints or critical points. And critical points are composed of locations where the derivative is zero or where the derivative does not exist. So if you made a flow chart, it would go into critical points, and critical points would flow into zero, a slope of zero, or a location where the function is not differentiable. So I'm just going to do a couple practice problems to warm us up. Here we have we're going to say a global max. Let me zoom out a little bit. Let's say at 0, 2 is a global max, which implies it's also a local max. And then here at -2, 0, and at 2, 0, at -2, 0, and 2, 0, we have two global minimums. Again, there can be more than one as long as they are tied. If they are tied, then they both count. So they're both global minimums, and because they're global, it implies that they are also local. So feel free to write local if you would like to. Here in this example, be careful, nothing is happening here. There's nothing happening there, and there's nothing happening here. So there are no maximums or minimums because they are open. They're hard to see, but they are, as I have the ability of zooming in here, there is nothing happening because they are open circles. What we do have, though, we have a local max. Everything to its left is lesser. And then here we have a local min. We do not have a global max or global min, just local max and local min. We'll say this happens at -1, 0, and at 1, 0. This location here is not a max or a min. There's also nothing happening here. Be careful. If there's no behavior, right? If there's no behavior left or right, there's nothing to talk about. So it's not a max nor a min. Number 3, looks like we have a global, we have at 0, 5, we have a global max, which implies that it is also a local max. There is nothing happening over here. I'm not going to label them anymore. I'm just going to say that there's nothing happening anywhere else. At 1, 2, we have a global max. We have a local min at 2, 0. We have a local, at -3, 0, we have a local max. We have a global min at 0, -1. This was a fixed interval, so on every fixed interval, we have to have a global max and a global min. at least one. Okay, according to our theorem. Our theorem that says if f is closed, we have a maximum and minimum value on the interval. Oh, it maybe not global, but yeah, it tends to be global on the endpoints or somewhere along the lines. Okay. There's a few more practice problems here. I'll let you do those on your own for practice. And the answers are in the back of the book. Don't forget, C, that's a location, right? Just because there's no dot there doesn't mean that the location doesn't exist. There is a location there. At each one of these, A, C1, C2, B, A, C, B, A, C, B, and so on. Okay. We talked about local minimums and maximums, critical points. Again, there are critical points and endpoints. That is where maximums and minimums can happen, or extreme values can happen. Here's your flow chart. Here's your extreme value. It goes into two categories. It goes into, endpoint. Let me try this again. We have endpoint or critical point. And the critical point is composed of the derivative equaling 0, or the derivative does not exist. So really, any three of these things could be an extreme value. Just be cautious that at a critical point, the derivative doesn't have to exist. Here's example 3, finding absolute extrema. We are looking for, obviously, this location. It's very clear that 0, 0 is an extreme value by the graph, right? But and on the interval -2, 3. So, and it's very clear that at this location we have so it looks like this is our x. These are our x's. It's an interval. So here's -2 to 3. So on that interval. So if I put in 3, 3 to the 2/3 is going to be the number 2. And you have the ability of checking your calculator. 2.08. This is, let's say, 3, 3 to the 2/3. So it's going to be 3 to the 2/3, which 3 to the 2/3 is equivalent to the cubic root of 3 squared, or the cubic root of 9. Let me just check to make sure that's equivalent. Yeah, the cubic root of 9. So let's just write this as the cubic root of 9 at that location. We have this is going to be a global max. Visually, we have a local max. And here we have at 0, 0, we have a global min. So visually, it's all, min. Visually, we can see them all here, and we really didn't even need the local max. It's going to be the cubic root of 4. It's -2 squared. It's the cubic root of 4. I'm just checking in the calculator. That is, yes, -2 to the 2/3. Yep, it's equivalent. So here you have the cubic root of -2 squared, which is a +4. So we have, again, we don't need that local max. Let's call it -2, comma. But what can we do to find these locations? So we're going to have to find the derivative first and set that equal to 0. We need to see if the derivative either does not exist, or if if there is a derivative of 0. As you see here, there is no location where the slope is going to be 0 of this function. So let's find that. So we're going to get a does not exist for this one. So let's find the derivative. The derivative is equal to 2/3 x to the negative 1/3. I drop the 2/3 down, take 1 away from the exponent. So I'm taking away 3/3, which gives me negative 1/3. And so what we have here is the derivative is equal to 2 over 3 to the 1/3. 3x to the 1/3. The 3 was always in the denominator. I moved the x down to the denominator. So the question is, when does this equal 0? So 0 equals 3x to the 1/3. 2 over 3x to the 1/3. Find my cross products. I get 0 equals 2. Or you can multiply both sides by 3 times x to the 1/3. Either way, when you do that, you get 0 equals 2. 0 never equals 2. This doesn't happen. So the derivative does not exist. The derivative does not exist at the location of 0. And how do I know it's 0? 0 is the only number I can't use here. So that's where I'm drawn to think that there's an issue at 0. Testing using my first derivative test, we have the location, the issue is 0. So I'll take a number, negative 1 and 1. I'll test these. I'll test negative 1 and 1. So let's put in negative 1. I evaluate negative 1. I get a negative within the derivative. The cubic root of negative 1 is negative 1. So I get negative 1 times 3, right? So if I do this, if I do the derivative at negative 1, I get negative 2/3. If I do the derivative at 1, I get positive 2/3. So I get a negative and a positive, meaning that there was a change in the derivative. The slope did change, which you can see here, it was negative and positive, the slope of these, which means that we have a global minimum there because it goes negative and positive. And then you just test your endpoints and you see which one's the highest. In this case, we get this one is definitely the highest value, so this would be our max. That's how you find them. It seems a little complicated, but you're just deriving, setting equal to 0, and seeing if it works out. Here's our next example. Let's find the derivative. Well, before we find the derivative, let's rewrite the function. Let's rewrite it as 1 over 4 minus x squared to the 1/2. And I could do quotient rule, but it's probably easier to just do product rule. Power rule. So let me rewrite again. I'll move this up to the numerator. Okay. And when I find the derivative, I need to be cautious that I do the chain rule as well. So the derivative, drop your exponent in front, keep everything the same, take away 1 from the exponent, which is taking away 2/2. And then don't forget to times by the chain link. The derivative of the inside is negative 2x. Don't forget to multiply by that chain link. So I'm going to clean this up. The derivative I'm going to rewrite. The derivative is equal to, so negative 2 times negative 1/2. I'm going to combine the first coefficient with the last negative 2x there, and I'm going to get a positive x because negative 1/2 times a negative 2 is a positive 1. So it's positive 1x. And then I have 4 minus x squared to the negative 3/2. Let's rewrite the derivative one more time. I'm going to rewrite it as the derivative is equal to x divided by 4 minus x squared to the positive 3/2. Awesome. Everything is where it needs to be. So let's evaluate. Let's find where the derivative is 0. So 0 equals x over 4 minus x squared to the 3/2. And find your cross products. You get 0 equals x. Well, that was easy. We found where the derivative is 0, and it's when x is 0. Take a look. We actually have a derivative there as 0 of 0. So the question really is, what is its minimum going to be as an output? So let's find f of 0. That's 1 over the square root of 4. That's 1/2. So I quickly found the output of this is 1/2. How do I know it's a minimum without seeing it? How do I know that's a global minimum? Well, I know I guess I can find out that it's a minimum. All I have to do is the first derivative test. Let's take, I'm running out of room here. Let me move everything, oh, whoops. Let me try that again. Let me see if I can move everything over without causing problems. Okay, the last thing I want to do is do the first derivative test, call it f dt. We have the location of 0. Let's try negative, negative 1. Did I use that color already? Let's do negative 1 and a positive 1. These are easy, hopefully, to calculate. Let's do a negative 1 in the first derivative. Be careful, make sure you put it back into here, the derivative. A negative 1 squared. In the denominator, you'll get a positive 1. It'll be 4 minus 1. Either negative 1 or 1, they go in, they get squared, they become positive. You have 4 minus 1 in either category, so you get 3 to the 3/2. That's great. Who cares what the number actually is? We know that the denominator will always be positive. But when you substitute that same negative 1 into the numerator, you get a negative. So you get a negative over a positive, which ends up being negative. So this one is negative. And for 1, when you substitute in, you get a positive over a positive, which makes it positive. So in this case, you just use a first derivative test to determine whether or not the function was increasing or decreasing. So it was decreasing, then it increased, and it had a slope of 0. So you can see that this is a minimum. How do we know it's global? Well, that comes down to the graph or figuring out if anything else is higher or lower than it. In this case, when you do look at those values that I said we didn't care about, those values would be higher than 1/2, which is what we found here. So because it's higher than the 1/2, it would tell us that it is a global, that everything else is higher than that. We also have global maximums here. We have a global max here and here at 2 and negative 2. So if I go, well, actually, we don't have any global maxes. Let's see what happens. The square root of 4 minus 4 equals the square root of 0 equals 0. You can't divide by 0. There are actually holes. I apologize. There are holes right here at those two values. So we don't know. We can't assume. There's nothing happening there. Nothing. Because of the fact that the square root of 0 is fine, but not having that in the denominator, you can't do that. Okay. Going on to the next example. Find the extreme values of this location of these functions. So find the extreme value. What we're going to do is we're going to find the derivative, and we see that the derivatives are different. So all we're going to do is see first if the derivative equals 0, and then we're also going to see if the derivatives differ at the location. If they differ at the location, there's going to be a critical point, which could be an extrema. If the derivative is 0, it could also be an extrema. Okay, this is not restricted, so we are only looking for extreme values that are local. We don't really need to find the, just because these end here doesn't mean that they end there. It doesn't give us an interval. So the first thing we want to do is derive. Let's do the derivative of the first one. It is going to be, the first function will be negative 4x. The derivative of the second function is going to be equal to 1. So the derivative of this is always 1, of the second function right here. That one is always 1. So does 0 ever equal 1? And the answer is no. So for this linear line, there's never a location where it's 0. So the derivative exists, it's the number 1. In this case, 0 equals negative 4x. So divide both sides by negative 4, we get 0 equals x. So this is going to have an extreme value when x is 0. This is going to have a, this one doesn't have any extreme value, but we see that when put together, does this derivative, hold on, let's see when these derivatives, do they equal each other at the location 1? Well, negative 4x, does that equal 1 when x is 1? Why am I saying 1? Well, that's what's right here. So does negative 4 equal 1? And that is not true. So this has an extreme value. They both have an extreme value when x is 1. And we see that the extreme value happens at 1 right here, and the extreme value also happens at 0. So we have we're going to say a maximum there at 1. So it's maximum 5 minus 2 times 1 squared equals 5 minus 2 equals 3. So we get 1 comma, what did I do here? Oh yeah, 1 comma 3. So locations 1 comma 3. And that is a local min. And then at my other location, I'm going to find out what my output is. I'm going to say f of 0. I'm going to do 5 minus 2 times 0. So it's 5. So this one is 0 comma 5. And that's a local max. Again, how do I know it's a max? Well, if I did my first derivative test, I can actually test it out. The location here is 0. I'm going to pick a number lesser. I'll pick the number negative 1, and I'll pick the number 1. Negative 1 times negative 4 is a positive 4. And then 1 times negative 4 is a negative. So again, we have a positive negative happening, so we know that it's going to be a max. In this case, the extreme value happens at 1 because we don't know exactly where, because we don't know, there's an issue. We see that there's a corner there. So at 1, so let's test the numbers before and after. Well, if I test the number 0, let me do the number 0. If I test the number 0, it has to happen in this function because 0 is less than 1. So if I test 0, I get 5, which is positive. I need, where's my derivative? Sorry. So I test this one because that correlates to that function. So I test that derivative and I get f prime of 0 equals negative 4 times 0. So it's 0. So I get 0. Well, I don't want to test 0. I'm sorry, because we know that that's a critical point. Let me test 1/2. My apologies. Let's test the number 1/2. So let's put in 1/2. Again, I can't test one that was already determined a critical point. That had a slope of 0. So that's going to give me a negative 2. And then I can test any number after that. So let's do the number 2. So put 2, but that one has to go into my other derivative. So it's going to be f prime of 2 equals 1. Well, that's always positive. So that one's positive. So we have a negative and a positive, making it negative positive, making it a minimum, which is why that one's a local minimum. All right. Again, a little bit of critical thinking, but we can use our first derivative test. We got to pick and choose the right one when we use it. We have to account for the fact that they don't have the same derivative from the left and from the right. So that was a little bit more work. Okay. The last one, you are not going to calculate by hand. Use a calc. Okay, how do you use the calculator on this? You are going to type it into you're going to go to y equals, then you are going to type in, you're going to click math. No, I'm sorry, y equals, you can type ln right there. You're going to hit the ln key. And then you are going to type in the best way to do it would be to type in ln. Sorry, you're going to hit the ln key in your calculator, and what you're going to put in to the calculator is going to be x divided by 1 plus x squared, all in parentheses, just like that. I would double. This set's not necessary, but just to be careful, you might as well get in the habit of separating the numerator fully from the denominator with 2 new sets of parentheses. And when you type that in, 1 plus x squared, close, you're going to type that in. And don't worry about the apps. Yes, we're going to have to worry about the absolute value. I'm sorry, we are going to have to throw absolute value around all of these. So we should have done the absolute value key. Just let me clean it up a little bit. Very, very cautious. Those results have to be the absolute value if you graph them. Well, let's see. Nope, I only got a result on the right-hand side. I did not receive a result on the left-hand side. So all of this was missing. So I'm going to go back and make sure my absolute value symbol goes there. And it didn't even look, it did look kind of like what's here. Yeah, for the most part. So I'm going to go back in. I'm going to insert some absolute value. That's going to be under the math key. Math number absolute x divided by 1 plus x squared. Be careful with your parentheses. I just messed up. Close, delete, delete, delete. Whoops. I have to type this all in again. ln math. So here, to get these, you have to type in, you have to go to math number abs for absolute. That's how you get those. I'm going to put them in. So parenthesis x, close, divided by parenthesis 1 plus x squared, close, graph. And yes, now I see both results. I see both this side, the left, and the right side. And in this case, it's hard to see. I'm going to have to zoom in. I'm going to make the window exactly what they told me to make the window. These are my X's and these are my Y's. You don't have to. I mean, you would have to play around with this. Actually, I'm going to do -4 to 4, and I'm going to do negative 3 to 1 to make it a little bit, even a little bit better. You can visually see that the maximum happens right about here. And how do you test that? You just go second calc. So here's a new operation. You're going to hit second calc, which is at the, well, second trace, which is the calc feature. It's going to bring it up. You're going to hit number 4, which is maximum. 4, which is maximum. Pick a number to the left and right. Oh, left bound, right there. Right bound. Oh, it does not want me to select it. Okay, left bound, right bound, guess. And you do that, and I get interesting. I get something a little bit different, but it might be because of my window. I get X is approximately 1.00005. And approximately negative 0.69, negative 0.693147. I still get that result. Maybe my calculator is a little different. Anything around here is okay though. And that's going to be a max. Global max. Looks like it's on the entire domain there. Okay. Awesome. You have a bunch of these. These are much more difficult. These are going to all be analytical methods. These are tough. I would use calculator for this one. I would do everything here on the calculator if you want to try. Okay, these are tough. You don't need to pass these in for homework. Do this for extra practice. Okay, you won't have anything that difficult. These, like numbers 19 through 22, you might see even 23 seems reasonable, but do these all by hand. Do these all by hand calculations. And these are, I would focus on this for the quiz. This for quiz 1, for Unit 6 quiz 1, and I would also focus on this does not have your, interesting, I don't know where your quiz review went. Maybe I didn't put any of the reviews in here. Okay, I must not have, I'll add them. I'm surprised they're not in here. So if we go to the quiz review, the quiz review solution key, yeah, and you're going to want to complete this as well. Do this assignment. Okay. All right, that's it for, yep. I'll post all the answer keys. Let me just do one more example, and then I will upload this video. So when you're focusing on these, here's what you're going to want to do. You're going to find these are all relative minimum and maximums. Let's see, and then we get into the cubic ones. So some of them might be difficult. So let's do a cubic one just for the heck of it. So you're going to find the derivative. So 3x squared plus 10x plus 3. You set the derivative equal to 0. So we get this. And not sure. I don't think there are any nice solutions. Let's see what number 7 has for an answer. Number 7 has this for an answer for minimums. So here's what you have to do. A little bit of quadratic formula. This is everything has to be set equal to 0. So here's your A, here's your B, and here's your C. So it's going to be negative b plus or minus square root b squared minus 4ac all over 2a. That is the location. Don't forget, it's an equation, x equals. So we're going to get x equals negative 10 plus or minus square root of 100 minus 4 times a times c. So 4 times 3 times 3. 4 times 9, 18, 27, 30, so 36. Right? 4 times 3 times 3. 4 times, whoops. 4 times 3 times 3, 36. Good. All over 2a, which is going to be 6. So x equals negative 10 plus or minus, we have the square root of 64 all over 6. So that equals, it's going to be x equals negative 10 plus or minus, let me move all this up. X equals negative 10 plus or minus 8 over 6. So that's going to give you negative 10 plus 8, which is negative 2, 6, or negative 10 minus 8, which is negative 18, 6. Okay, which ends up being the locations negative 1/3 and the location negative 3. So these two are your x's. So let's say x is equivalent to negative 1/3 and negative 3. So far, we have the locations of the x value of the relative minimum and the relative maximum. Right? We don't know if they're minimum or maximum. We are going to have to do the first derivative test. So let's do the first derivative test. So let's take our first derivative and our values, negative 3, negative 1/3, and negative 3. Here's negative 3. Here's negative 1/3. Let's find a couple numbers that work around it. Well, I could pick 0, negative 1, and negative 4. So I go to my first derivative, and I evaluate those numbers in. When I put in 0, I get a positive 3 right here. So I get a positive, positive. If I put in negative 1, I get 3 minus 10, which is negative 7, because negative 1 squared is 1. So I get 3 plus 10. Negative 1 squared is 3 plus, but it would be minus 10, so it's negative 7 plus 3, which is negative 4. So this is a negative. If I put in negative 4, I'm going to do some algebra. Negative 4 squared is 16, so 16 times 3 is 48, and that's going to be minus 40, so that's 8 plus 3 is 11, so it's a positive 11. So my function goes positive, negative, positive, which means that at negative 3, comma something, I have a max. And at negative 1/3, I have a min. Oops, I have a min. They're local because a cubic function. And to find outputs, you just put it into the original function. So you can get a decimal for this. You don't have to go crazy. Just type in your x into your y equals. I'm just going to put their answer. If you evaluate negative 1/3, it looks like you get negative 148 over 27. Negative 148 over 27. Negative 1, oh, sorry. Negative 148 over 27. And if you substitute in negative 3, you get the answer of 4. And that's it. So focus on the CUDA work. I did one of the harder ones, but focus on CUDA and your quiz review. And our quiz will be on Monday. You have all Thursday to watch this video and practice. Again, I hope you watch it before that, and then you can practice all day, all class period for the quiz. And I'll answer questions that you have on Monday before the quiz. Okay, feel free to also stop by during lunch, during PLT, off roll, whatever you need. All right, see you later. Bye.